Hi students, good morning all of you. Hope you are all doing good. Welcome to lecture 11 in Theory of Equations. Hope you have watched the previous 10 lectures in this topic. In this lecture, I will be discussing how to solve polynomial equations with complex roots and how to solve polynomial equations with irrational roots. Let us solve some problems. Here is our first problem in this lecture. Show that the equation a square by x minus a dash plus b square by x minus b dash plus c square by x minus c dash and so on up to k square by x minus k dash is equal to x minus m, where a comma b comma c and so on up to k comma m and a dash, b dash, c dash and so on up to k dash are all real numbers, cannot have a non-real root. That means you have to show that this above equation, the given equation cannot have a complex root. This is what we have to show in this particular problem. In the last lecture we have solved a similar type of a problem. This is a generalized version of it. Okay, let us try to prove this. Proof. Given equation is, let us write the given equation: a square divided by x minus a dash plus b square divided by x minus b dash and so on up to k square divided by x minus k dash is equal to x minus m. Now let us try to rewrite this. This is a square into x minus b dash into x minus c dash and so on up to x minus k dash plus b square into x minus a dash, x minus c dash and so on up to x minus k dash and so on, k square into x minus a dash, x minus b dash and so on up to x minus l dash. Whole divided by the LCM is x minus a dash into x minus b dash and so on up to x minus k dash is equal to x minus m. Now let me rearrange the terms. This is a square into x minus b dash into x minus c dash and so on to x minus k dash plus b square into x minus a dash into x minus c dash and so on up to x minus k dash and so on. This is equal to the last term. Let me write k square into x minus a dash, x minus b dash and so on up to x minus l dash is equal to x minus a dash into x minus b dash into and so on up to x minus k dash into x minus m. Okay, so the above equation is a polynomial equation of degree m. Okay, and with real coefficients, because it is given that a, b, c and so on up to k comma m, a dash, b dash, c dash and so on up to k dash are all real numbers. So the given equation is a polynomial equation of degree m with real coefficients. But to solve this problem we will use the given form itself. Let us continue the problem here. Here is the continuation. Let p plus iq be a complex number which is a root of the given equation. Okay, so if p plus iq is a root, then p plus iq satisfies the given equation. So let me substitute that is a square divided by p plus iq minus a dash plus b square divided by p plus iq minus b dash, and so on. K square divided by p plus iq minus k dash is equal to p plus iq minus m. You call this as equation 2. As we did in the last problem, we do take the conjugate here. Take the conjugate on both sides. We get a square divided by p minus a dash minus iq plus b square divided by p minus b dash minus iq, and so on up to k square divided by p minus k dash minus iq is equal to p minus m minus iq. Call this equation 3. If I subtract equation 3 from equation 2, we get a square into 1 divided by p minus a dash plus iq minus 1 divided by p minus a dash minus iq plus b square into 1 divided by p minus b dash plus iq minus 1 divided by p minus b dash minus iq, and so on up to, if I subtract these two, pp gets cancelled and mm gets cancelled, this becomes 2 into iq. Okay, let us continue the problem here. Here is the continuation. Then this becomes a square into, this is p minus I, this is p minus a dash minus iq minus p minus a dash plus iq divided by p minus a dash whole square plus q square plus b square into p minus b dash minus iq minus p minus b dash plus iq divided by p minus b dash whole square plus q square, and so on. K square into p minus k dash minus iq minus p minus k dash plus iq divided by p minus k dash whole square plus q square is equal to 2 into iq. Now this is equal to, if I simplify this term, then I get, in the denominator I will be having p minus a dash square plus q square. This is going to be minus 2iq plus b square into minus 2iq divided by p minus b dash whole square plus q square, and so on, k square into minus 2iq divided by p minus k dash whole square plus q square is equal to 2 into iq. Now in all these terms I can take common 2iq. I bring this term this side, then I get a square divided by p minus a dash whole square plus q square plus b square divided by p minus b dash whole square plus q square, and so on, k square divided by p minus k dash whole square plus q square plus 1 is equal to 0. Here the product of two terms becomes 0. This implies either this is equal to 0 or this term is equal to 0. Anyway, this term cannot be 0 because it contains all the square terms plus 1. This cannot be 0. This implies minus 2iq is equal to 0 implies q is equal to 0. That means in the complex number p plus iq is equal to p plus I into 0, that becomes p. So this implies the complex number, any complex number, okay. So for the given equation, the roots cannot be complex number. The roots cannot be complex number, but only reals. Okay. Here is the conclusion of the theorem. Okay. Hope you have understood this. In the next slide, we will be discussing a theorem. Here is the statement of the theorem. Let f of x be a polynomial of a degree n greater than 0 with rational coefficients, and let a, b be rational numbers, b greater than 0 and root b is irrational. Then a plus root b is a root of f of x is equal to 0 if and only if a minus root b is a root of f of x is equal to 0. Let us try to understand this theorem. You are given a polynomial of degree n greater than 0 with the rational coefficients. That means for a given polynomial, all the coefficients are rational. And these a comma b are rational numbers, b greater than 0 such that root b is irrational. That means root b is a surd. Then what they are telling is a plus root b is a root of f of x if and only if a minus root b is a root of f of x is equal to 0. So that is, if a plus root b is a root of f of x is equal to 0, then a minus root b is also a root of f of x is equal to 0, vice versa. It is similar to that of complex root occurring in the conjugate pair for a polynomial with real coefficients. We have seen in the last lecture, for a polynomial with real coefficients, a plus ib is a root if and only if a minus ib is also a root. It is just similar to that of that result. So let us see some example for this. Consider f of x is equal to x minus root 3 into x plus root 3 into x minus 1. This can be written as x square plus 1 into x minus 1. If you look at this equation, all the coefficients are rational and the roots of this equation are plus or minus root 3 comma 1, and you can see that root 3 comma minus root 3 are both are roots of this equation. Of course, the coefficients are all rational coefficients. The coefficients are all rational coefficients. Now let us look at a non-example. Here is a non-example. Consider g of x is equal to x minus root 3 into x minus 1, x square minus of root 3 plus 1 into x plus root 3. If I take the multiplication, if I do the multiplication, I will be getting this quadratic expression. Now, what are the roots of g of x? The roots of g of x are root 3 comma 1, but minus root 3 is not a root of g of x is equal to 0. Why? Because the coefficients of g of x are not all rational. There are some coefficients which are rational and some coefficients which are irrational. That's why the conclusion of the above theorem is failed in this particular case. Hope you have understood the statement of the theorem through this example. Okay. We are not getting into the proof of this theorem. In the next slide, I will be discussing a similar result. Now, let me discuss that result here. Here is the statement of the result. Let f of x be a polynomial of degree n greater than 0 with the rational coefficients, and let a comma b be rational numbers so that a comma b greater than 0 and root a comma root b are irrational. Then root a plus root b is a root of f of x is equal to 0 implies root a minus root b minus root a plus root b minus root a minus root b are all the roots of f of x is equal to 0. That means if one of these four numbers is a root of f of x is equal to 0, then the other three numbers are also the roots of f of x is equal to 0. That means whenever you are given a polynomial of degree n with all rational coefficients and where root a comma root b are irrational, then one among these four roots, if at all one among these four roots is a root of f of x is equal to 0, then the other three numbers are also roots of f of x is equal to 0. This is an important conclusion. Okay. Let us solve one more problem. Here is our next problem. Form a polynomial equation with real coefficients whose roots are 4 root 3 comma 5 plus 2i. Now, if the same question, it is just similar to that of the previous question, how does the solution changes? So in the previous case we have been asked the rational coefficients. Now in this case we have been asked the real coefficients. Okay, let f of x be a polynomial required polynomial with real coefficients. Okay, it is given that four root 3 comma 5 plus 2i are roots of f of x is equal to 0. Now, by a theorem studied in the last lecture, previous lecture, if 5 plus 2i is a root of f of x is equal to 0, then 5 minus 2i is also a root of f of x is equal to 0. This is the conclusion, and you cannot claim here minus 4 root 3 is also a root, because they are not insisting on the rational coefficients. So that's why, therefore, your f of x is equal to x minus 4 root 3 into x minus 5 plus 2i into x minus 5 minus 2i. So that is equal to x minus 4 root 3 into is x minus 5 minus 2i into x minus 5 plus 2i, that is equal to x minus 4 root 3 into this is x minus 5 whole square plus 2 square. So that is equal to x minus 4 root 3 into x square minus 10x plus 29. So if we expand it, we will get that answer. So the difference between the last problem and this problem is, they have asked in the last problem polynomial equation with the rational coefficients. Here we have been asked with real coefficients. So this is the change actually. You will not get x plus 4 root 3 as a root of it, okay, because they are insisting on only real coefficients, not the rational coefficients. If at all they have asked rational coefficients, then x plus 4 root 3 is also a root of it, okay. Let us discuss one more problem. Here is our next problem. Solve x to the power 4 minus 6x cube plus 11x square minus 10x plus 2, given that 2 plus root 3 is a root of the equation. That means you are given a quadratic equation and one root. So you are asked to solve this equation. Here is the solution. Let f of x is equal to x to the power 4 minus 6x cube plus 11x square minus 10x plus 2. Observe that all the coefficients of f of x are rational. It is given that it is given that 2 plus root 3 is a root of f of x is equal to 0. So by a theorem we have studied, if 2 plus root 3 is a root of f of x is equal to 0, then 2 minus root 3 is also a root of f of x is equal to 0. We have studied this theorem in this lecture itself. So this implies both 2 plus or minus root 3 are roots of f of x is equal to 0. This implies x minus 2 plus root 3 and into x minus 2 minus root 3 is a factor of f of x is equal to 0. So let me expand it. So this becomes x minus 2 minus root 3 into x minus 2 plus root 3 is a factor. So this is equal to x minus 2 whole square minus root 3 whole square, that is equal to x square minus 4x plus 4 minus 3 is plus 1 is a factor of f of x is equal to 0. Let us continue in the next page. Here is the continuation. So we have got x square minus 4x plus 1 is a factor of f of x is equal to 0. Now let us try to find out the remaining factor of f of x. We use the Horner synthetic division to find out that. Let me write the coefficients in the order. So 1 minus 6, 11 minus 10 and 2 here. So let me write pq values. P value is 4 and q value is minus 1. Let me write it here. So it is 4 and minus 1. So 0 and 0 here. So this becomes 1. 4 into 1 is 4 and still it is 0. So this is minus 2. 4 into minus 2 is minus 8 and minus 1 into 1 is minus 1. So this becomes 2 actually. Now 4 into 2 is 8 and minus 1 into minus 2 is 2. So 8 plus 2 10, 10 minus 10 is 0 and this is anyway 0 and minus 1 into 2 is minus 2 and this becomes 0. Therefore this f of x can be written as x square minus 4x plus 1 into x square minus 2x plus 2. Let us solve this. Now let us solve this equation. Let us solve x square minus 2x plus 2 is equal to 0. The roots are minus of minus 2 plus or minus b square, that is 4 minus 4 into a into c. So it is 4 into 2 divided by 2. So that is equal to 2 plus or minus 4 minus 8, that is minus 8. So minus 4 divided by 2. So that is equal to 2 plus or minus 2i divided by 2. This is equal to 1 plus or minus I. So the roots of this other factor are 1 plus or minus I. Therefore the roots of f of x is equal to 0 or 2 plus or minus root 3 comma 1 plus or minus. These are the roots of the given equation. Let us solve one more problem. Here is our next problem. Solve the equation x to the power 4 plus 2x cube minus 16x square minus 22x plus 7 is equal to 0, given that 2 minus root 3 is one of its roots. Let us find out the solution for this. Here is the solution. Let f of x is equal to x to the power 4 plus 2x cube minus 16x square minus 22x plus 7. Okay, observe that roots of coefficients of f of x are rational. Okay, so it is given that two minus root 3 is a root of f of x is equal to 0. So by a theorem we have studied already. By theorem, if 2 minus root 3 is a root of f of x is equal to 0, then 2 plus root 3 is a root of f of x is equal to 0. So therefore both 2 plus or minus root 3 are roots of f of x is equal to 0. So this implies x minus 2 x minus of 2 plus root 3 into x minus of 2 minus root 3, that is equal to x minus 2 whole square minus root 3 whole square, that is equal to x square minus 4x plus 1 is a factor of f of x is equal to 0. Now let me do the Horner synthetic division to find out the remaining factor. So let us write the coefficients. 1, here it is 2, minus 16, minus 22 and 7 here. We have got x square minus 4x plus 1 as a factor of f of x is equal to 0. So let me write the p q values. So p value is 4 and q value is minus 1, and this is 0 and this is 0. So 1 plus 0 plus 0 is 1. So 4 into 1 is 4, and is minus 1 into 1 is 1 minus 1. So 2 plus 4 is 6, 6 minus 1 is 5. 4 into 5 is 20, and minus 1 into 5 is minus 5. So this becomes minus 1. 4 into minus 1 is minus 4, and minus 1 into 5, minus 1 into minus 1, minus 1 into 5 is minus 5. Let us continue the problem in this page. So we have got x square minus 4x plus 1 as a factor of f of x is equal to 0. So let us find out the other factor of f of x using Horner synthetic division. Let me draw a vertical line and write the coefficients. 1, 2, minus 16, minus 22 and 7. So this is x to the power 4 coefficient, this is x cube coefficient, this is x square coefficient, this is x coefficient, and this is x to the power 0 coefficient. Let me write the pq values. P value is 4 and q value is -1 here. So 0, 0. In the beginning I am putting 2 zeros and add. So 4 into 4 is 0 and this is 0. 4 into 4 plus 2 is 6. So 4 into 6 is 24. Minus 1 into 1 is -1. So 24 minus 17. So 3 plus 4 is 7. So it is 7. 4 into 7 is 28. And minus 1 into 6 is -6. 28 minus 28, that becomes 0. So this is anyway 0. Minus 1 into 7 is -7, that becomes 0. So we have got the remainder as 0, so it is a factor of it. Therefore this f of x can be written as x square minus 4x plus 1 into x square plus 6x plus 7. Okay, let us solve x square plus 6x plus 7 is equal to 0. The roots are -6 plus or minus b square. 36 minus 4 into 7 divided by 2. Divided by 2, that is -6 plus or minus under root 36 minus 48. Sorry, 7 into 4 is 28. So this becomes 8 divided by 2. So it is -6 plus or minus 2 root 2 divided by 2. So that is -3 plus or minus root 2. Okay, so therefore the roots of the given equation are 2 plus or minus root 3 comma -3 plus or minus root 2. Okay, let us solve one more problem. Here is our next problem. Solve the equation 3x to the power 5 minus 4x to the power 4 minus 42x cube plus 56x square plus 27x minus 36 is equal to 0, given that root 2 plus root 5 is one of its roots. We have to solve this polynomial equation. Here is the solution. Let f of x is equal to 3x to the power 5 minus 4x to the power 4 minus 42x cube plus 56x square plus 27x minus 36. Okay, so observe that all the coefficients of f of x are rational, and it is given that root 2 plus root 5 is a root of f of x is equal to 0. By theorem we have if root 2 plus root 5 is a root of f of x is equal to 0, then root 2 minus root 5 comma minus root 2 plus root 5 comma minus root 2 minus root 5 are roots of f of x is equal to 0. So we have got 4 roots of f of x is equal to 0. Let alpha be the remaining root. So let us consider the sum notation. S1 is equal to root 2 plus root 5 plus root 2 minus root 5 minus root 2 plus root 5 minus root 2 minus root 5 plus alpha is equal to minus of minus 4 divided by 3, that is equal to 4 by 3. So all these things gets cancelled. So what do we get is alpha is equal to 4 by 3. So the roots of the given equation are so plus or minus root 2 plus or minus root 5 comma 4 by 3. These are the roots of the given equation. Okay. Let us discuss one more problem here. Here is our next problem. Form the polynomial equation with rational coefficients whose roots are I minus root 5. Okay. So let us try to solve this problem. Here is the solution. Let f of x be a required polynomial with the rational coefficients. That is very, very important. Rational coefficients. It is given that I minus root 5 is a root of f of x is equal to 0. So for the coefficients to be real, coefficients of f of x is equal to 0 to be real, if I minus root 5 is a root, then I plus root 5 comma minus I plus root 5 comma minus I minus root 5 are also the roots of f of x is equal to 0. It is very similar to that of the result that we have studied. If root a plus root b is a root of a polynomial equation f of x is equal to 0, then root a minus root b minus root a minus root b minus root a plus root b are also the roots of f of x is equal to 0. It is just similar to that of this. So then f of x is equal to x minus of I plus root 5 into x minus of I minus root 5 into x minus of minus I plus root 5 into x minus of I minus root 5. So this is equal to now let me consider these two. And let me consider these two polynomials. So this is x minus root 5 minus I into x minus root 5 plus I, and this is x plus root 5 minus I into x plus root 5 plus I. So it is the form a plus ib, a minus ib. So this is x minus root 5 whole square plus 1, and this is x plus root 5 whole square plus 1. That is equal to x square minus 2 root 5x plus root 5 whole square is 5 plus 1, that is equal to 6. X square plus 2 root 5x plus 6. So if I expand it, then this becomes x to the power 4 plus x cube into, so x cube means 2 root 5 and x should multiply with x square. This is minus 2 root 5. Now plus x square coefficient, let us find out. X square means 6 and minus 2 root 5 into 2 root 5 minus 4 into 5 minus 20 plus 6 plus x coefficient. So minus 2 root 5 into 6, so it is minus 12 root 5 plus 12 root 5 plus 36. So the required equation will be x to the power 4, this becomes 0, 6 plus 6 12, 12 minus 20 is minus 8, so minus 8 into x square plus x, this is 0 plus 36. So the required polynomial with the rational coefficients is x to the power 4 minus 8x square plus 36. Okay, let us solve one more problem here. Here is our next problem. Form the polynomial equation with rational coefficients whose roots are minus root 3 plus I root 2. Let us find out the solution for this. Here is the solution. Let f of x be the required polynomial with rational coefficients. Okay, it is given that minus root 3 plus I root 2 is a root of f of x is equal to 0. So by a theorem which is stated earlier, if minus root 3 plus I root 2 is a root of f of x is equal to 0, then minus root 3 minus I root 2 root 3 plus I root 2 comma root 3 minus I root 2 are also roots of f of x is equal to 0. Therefore, your f of x is equal to x minus of minus root 3 plus I root 2 into x minus of minus root 3 minus I root 2 into x minus of root 3 plus I root 2 into x minus of root 3 minus I root 2. Okay, now this is, let us multiply these four products. So let me multiply these two. This becomes x plus root 3 minus I root 2 into x plus root 3 plus I root 2, and this is x minus root 3 minus I root 2 into x minus root 3 plus I root 2. So x plus root 3 minus I root 2 plus I root 2, this is x plus root 3 whole square plus root 2 whole square into this is x minus root 3 whole square plus root 2 whole square, that is equal to x square plus 2 root 3x plus root 3 whole square is 3 plus 2 is 5, and this is x square minus 2 root 3x plus 5. Now if I multiply this becomes x to the power 4 plus x cube into minus 2 root 3 plus 2 root 3 plus x square into 5 2 root 3 into minus 2 root 3, that is minus 4 into 3, that is minus 12 plus 5 plus x coefficient 2 root 3 into 5, that is 10 root 3, and 5 into minus 10 root 3, so this is minus 10 root 3 plus 25. So that is equal to x to the power 4, this is anyway 0, so 5 plus 5 10, 10 minus 12 is minus 2, so this is minus 2x square plus 25. So this is our required polynomial with the rational coefficients. Yeah. Okay.